Okay, then we've developed a new microscopy to study the charge carriers called pattern illumination, kind of time-resolved phase microscopy. I call this one PIPM method. And first, hardware things, meaning what's the concept of this microscope and how to improve the time resolution, and why do we need the pattern illumination. Okay, so first I'm going to talk about this one. So here's a particulate film. So what we do is we illuminate the light with a pattern like this. So at the position where the light intensity is strong, electrons and the holes, charge carriers are generated. And then these charge carriers can move around. And what we do is we observe the refractive index change due to the charge carrier distribution. And then when these charge carriers moves around, these refractive index spot gradually obscured or blurred, right? And then as time passed, the refractive index could be like this pattern. So what we can do is by analyzing this kind of blurring, charge carrier transport or decay could be observed. And also by using this kind of pattern illumination, due to the contrast illumination, we hope that we could improve the SN ratio of the signal, because the refractive index due to the charge carriers are usually very small. So to demonstrate this, if this concept will work fine or not, we started from the stripe pattern of the light illumination at first. So just a one-dimensional light pattern. Right? So what we did is here's a sample, and somehow we illuminate the sample with a stripe pattern. Then photoinduced change is induced. In this case, charge carriers are generated, and illuminate another light called a probe light. And then by using the imaging setup, we observe what's kind of change happening inside the sample by the camera. And during the charge carrier motion or decay, we can observe by the image. Here's a setup. The pump pulse for excitation of charge carriers are patterned by using in this case, transmission grating. So it's a sort of the pattern of the glass, but now these days we are using the different device to making a pattern. But the principle is saying this pattern of light is illuminated and down to the sample position, and to illuminate the stripe pattern in this case. So when you use the stripe pattern, it is called a transient grating because the temporal refractive index grating is formed here. And then at the back side of the sample, we make imaging setup on the camera to monitor what happened inside the sample. Okay. In actual setup, in this sample, we can see this kind of refractive index pattern, and to reduce the burden of the computers, we cut off the center of the region, and then we obtain the refractive index image by time with a high resolution camera. So here's the first demonstration. In this setup, pump light illuminates a sample, and probe light is illuminated, and then the image down to the camera. And first, we use MBBA, which is photoresponsive liquid crystal, because it gives a very strong refractive index response. So here's and then what happened here is due to the refractive index change, it's going to like this. And what happened here is this. So with 1 millisecond time resolution, we can see the refractive index pattern changing. But still, it's not clear much. So what we did for the next step is to enhance the refractive index sensitivity with glass here. So what we are doing is basically part of the light is phase shifted, and then interfere using the interference. We can obtain the refractive index image much with higher sensitivity, and then we can obtain the response like this very high contrast for the photoresponsive materials. And then now move on to the for semiconductor material measurement, and then of course we need to make a very high time resolution, because the charge carrier decay is on order picosecond, nanosecond, microsecond order, or millisecond order. So and also we use a DMD mirror, which gives different patterns of light. And what we did is we use another nanosecond laser as illumination for light, and then these two are controlled. So in a sense, pump probe imaging method, meaning when time is 0 nanosecond, pump light is illuminated, and if we need the image at t equal t nanosecond, this probe pulse illuminated at after t nanosecond of this one. So we can always obtain the image at t nanosecond using this. And then we can scan this time and obtain and reconstruct the image again. So what we can obtain here, here's the real phase image of the TiO2 sample, and here's a response we can obtain. So it's now nanosecond, 10 nanosecond, and 100 nanosecond order. So various time orders we can obtain the refractive index image using this, and gradually decaying on the order of microsecond. It's now almost totally lost, about hundreds of microsecond. So now the time resolution is 3 nanosecond with very high contrast imaging of the refractive index, and very good to see. And here's the real optical setup here now, the latest optical setup. So pump light is illuminated to the DMD mirror, and then this DMD mirror, after reflection of DMD mirror, pattern light is illuminated to the sample. And for the imaging part of here, the microscopic optics using the imaging lens, and then we can obtain the microscopic image to the CMOS camera. So before making the setup, the signal response was like this level, but these days now for the stripe pattern of the illumination, we can obtain this level of contrast of the refractive index image, and also we can generate this kind of dot pattern excitation of the charge carriers for TiO2, and with a very high time resolution, like on the order of the few nanosecond. Okay, so now the hardware things, we can have spatial resolution or 2 or 3 micron, and temporal resolution as about 3 nanosecond, and with a very high SN ratio.